Welcome back to another thrilling episode of Math 168 Statistics. This is Professor Needing. Today we're talking about experimental and observational studies, section 1.3. So get yourself a snack, hold on, and let's go. I'm going to get rid of myself there. Don't need to see me. So in section 1.3, we're going to talk about association versus causation. We're going to talk about the confounding variables. And we're going to look at an observational study versus an experimental study. We're also going to talk about the randomized experiment. So let's do a little review to get started with. To estimate the proportion of students who support a smoke-free campus, you compute the proportion that say yes after responding to an email sent to all students asking, do you support a smoke-free campus? The data collected is, take a moment, read the choices, stall the video, and then come back and see if you're right. Okay, here we go. So first of all, a couple of things that I see real quick like that we probably should take a look at. So we're looking at proportion. That's nice. Okay. And we're going to calculate from that proportion. Oops, I did a strike through instead of a markup. Here we go. I am just messing this up totally. I have to get my text highlighter. I have to get a color on my text highlighter. And then I have to highlight. There we go. The proportion of students who support this. You compute a proportion from a sample. Hey, you're doing good so far. But then you fall down because you sent an email out. Okay, you collect the data, all the data that's being sent to you. However, first of all, it is a biased situation because the volunteer samples are almost always biased. You cannot send an email and allow people to respond as they feel like it. You see email, you see volunteer basis, you see any of those words, and you may as well just write the word bias next to it. Association versus causation. Time for something a little new here. So when we talk about an association and a causation, two variables are associated if the value of one variable tends to be related to the value of the other variable. Associated. As something increases, something else increases, but it's just by association. It just happens. However, if two things are causally associated, if changing the value of the explanatory, remember that's on the x-axis and that's the one that's introduced first, influences the value of the response variable, and remember that's the y variable, the one that comes second, then you have a causal association. For instance, the temperature increases as the hours of the day increase in the AM. So as the sun comes up, then the sun is the explanatory, the increase in the temperature is the response, and there is a causal association between the sun, where it is in the sky, and how warm it is in the day. However, when we look at two variables that are associated, just because one changes and the other changes doesn't mean that one causes the other to change. And I'll give you some examples of that. There are some explanatory and response. For each of the following, we want to identify the explanatory and the response variable. So we're going to do that again. Does the headline imply an association, a causation, or neither one? Okay, so studies show that taking a practice exam increases your score on an exam. Okay, so first of all, we're supposed to find the explanatory and the response. So let me do a little bit of underlining here. Let me do a little bit of drawing, and let me grab a color. So in the first one, I probably should go something besides blue since we already have it. We have a practice exam. Okay, a practice exam is going to occur before an actual examination. So when we look at the practice examination, we are definitely going to call that our explanatory. When we look at the examination, it's definitely going to be our response. Now the question is, when we look at this, do we feel that it is causal, or do we feel that it is neither, or is just an association? What is it? Well, I think that taking a practice exam probably has an influence upon an exam. So we would have down here that this would be a causal effect. Practice exam certainly could have a causal influence on the score you receive on an examination. Second, a family with many cars tends to also own many TVs. Okay, so let me get my tool here. We're going to do a little drawing again here. Let's change to maybe, let's use red. So many cars is our explanatory, and owning many TVs is our response. And we'll mark that down on there so we actually have that particular piece on it. So again, we'll put EX, explanatory, and TV's response. Now, the question is, do you think because I have a TV, I own a lot of cars? Do you think that's a causal effect? So I go down the store, I buy a new car, and ooh, you got a new TV with it. Okay, well, that's why I have another TV. This one doesn't cause the other. Now, are they associated? Well, sure, they could be associated. They're associated based on the fact that um, I probably own more TV sets because I own more cars, and it probably has something to do with wealth. It has something to do with the status of a person and what they actually physically own. I'm going to try and make a comment here and see how this works out. I'm going to comment on this one right here, and comment's going to come over, and this is just going to be an association. Effect or the relationship between having a lot of cars and having a lot of TVs is going to be one of purely association. Whereas up here, when I had this one up here, this one was definitely causal. Number 3, among college students, no link found between number of Facebook friends and size of college. Okay, so first of all, let's identify the two things here. So we have two things going on. And let me drawing tools. So we have no link found between, and it doesn't matter link or not link, we're just talking about things. So we have number of Facebook friends, and let's put that down as happening, and then size of college. Okay, so the question is which one takes place first, right? Which one's explanatory? Would we say that the number of Facebook's friends explains how large your college is, or we say that the size of your college explains how many Facebook friends you have? And I think that you get that it's the second one, right? So the college itself will be the explanatory, and the number of Facebook friends will actually be the response. Now, again, do we think this is causal, or do we think this is just simply association, or do we think there's nothing going on at all happening there? Well, some people would say, well, okay, well, I have more Facebook friends because the college that I have is larger and I'm trying to keep tabs with all the people associated with it. If I go to a big college, do I have to have more Facebook friends? Not necessarily. You're talking to a guy who has no Facebook, no anything. So, and I went to a large college and I still didn't have any. So it's not going to cause me to have Facebook friends, but it certainly could be associated to that. So again, we would have an association that happens between those. I do believe that there'd be an association between the size of a college and the number of Facebook friends. And we could always pluck out an outlier somewhere where we didn't have that happening at all, like me. But at the same time, though, we're going to have some kind of association there. We're going to have a pattern. Cell phone radiation leads to deaths in honeybees. Okay, so let's pick out the explanatory here. So first of all, cell phone radiation maybe has a response of deaths in bees, or deaths in bees somehow cause cell phone radiation. I think that we have to go with the phone radiation as the explanatory and the death in honeybees as the response. Okay. Now, there have been studies done in which, and you may or may not know them, to where there is an association between radiation and the death of honeybees. And we can look at this and we could say, okay, there clearly could be an association, but we could also say clearly there could be a causal association between these two. Number 5, want to lose weight, eat more fiber. So it's just basically a statement. which one would happen to happen first is really what you want to look at for the explanatory. Well, the explanatory was you better eat the fiber if you want to lose the weight. The lose weight's not going to cause you to eat the fiber. The eating of the fiber is going to maybe cause you to lose the weight. Not quite sure it will or it won't. We're not trying to prove whether it does or whether it does not. So eating of fiber, explanatory. Losing weight, a responsive or response variable. Question is, just associated or are they causal? Well, we don't have any data to support that, and I've never seen any data to support that. Maybe there is some data to support that. If you can give me some data, then we can talk about causal. However, though, association, definitely, yes. Causal, to be determined. How's that? Cat owners tend to be more educated than dog owners. Okay, well, this is something that appears not to be a statement. So again, number 5 is association. And if we can get some data, we'll come up with a causal. But number 6, cat owners tend to be more educated than dog owners. Okay, well, what are we talking about here? First of all, we would need something to compare to something else. So first of all, we don't have an explanatory. All we have is a statement saying one thing tends to be more than another thing, and this one would be a neither of anything going on. We can't even really identify an explanatory and a response here. If we can't even find an explanatory and response, then we can't assign association causal. We would be neither. A confounding variable. A third variable that's associated with both the explanatory variable and the response variable is called a confounding variable. So we confound something when we kind of mess up the data, if you will. It says a confounding variable can offer a plausible explanation for an association between the explanatory and the response variable. So if I can go back to the honeybee one, and if in the honeybee one, I can go in and I can find a confounding variable that has something to do with honeybees dying and cell phone radiation, basically I can confound the results of what's going on. So could there be an association without causal effect? Sure, there could be. Maybe besides cell phone radiation, maybe because of the places where cell phones are used the most, metropolitan areas. Maybe it's the pollution within those areas that's really killing the honeybees, or maybe it's the hardscape that's killing the honeybees because they don't have a home. So if there's a third confounding variable in there, then that deletes it down to an association. There's always an association. If you see one thing going up and another thing going up, or some up and down, then it's definitely an association. You don't have to have causal effect for an association. But for an association, you have to have some proof if you're going to move into the causal area. Whenever confounding variables are present or may be present, a causal association cannot be determined. Okay. For instance, let's look at this one. And let's get a little more in depth in and try and make some better statements here. So I have this chart, and on the x-axis, which would be the explanatory, and I'm gonna type that in so we are using the right words here. This is the explanatory on the x-axis, and over here on the y-axis is the response, which is life expectancy. We have some data, and we have some data from some countries, and we have TVs and life expectancy. So what this chart is attempting to ask me is by the TVs per 1,000 people. So it appears as I own more TVs, I have a longer life expectancy. I mean, the line is going uphill, the trending line, which we'll cover in section 2.5 and 2.6. It's got an awesome R value right here. This R value is phenomenal. You don't know about an R value yet, but that R value is pretty amazing. R 0.74. And it appears that like I said, as I go to the right, my age seems to increase, my life expectancy. So I should run out and buy more TV so I live longer, if I want to live longer, right? Well, the question is, association does not imply causation. Well, this is clearly an association, okay? And this is associated data, and it's going uphill, and it's trending in a linear pattern, and all those kinds of things we'll talk about later. But it doesn't necessarily cause anything. And I think we're all intelligent enough to know that buying more TVs doesn't make us live longer. Probably more than likely, the confounding variable in the situation is that in a area which people own more television sets, there's a higher access to money. And because they live a life which they have access to money, they have access to healthcare, they have access to other things which extend their life a little bit further. So there are confounding variables associated with owning the television sets that are influencing the life expectancy. And here's a nice layout of that. Wealth could be associated with the number of TVs, but wealth could also be hooked to life expectancy because you have access to all those other things that make life expectancy elongate itself. A confounding variable. For each of the following relationships, identify a possible confounding variable. More ice cream sales have been linked to more deaths by drowning. I actually read that one, and I've used that one before in a number of different avenues. So there's a study out there that there's all these ice cream sales, and as ice cream sales went up, death by drowning increased, and there was tons of people drowning because people were eating ice cream. And so we can make a data set that says, hey, if you eat ice cream, you're going to drown. Well, no, not really. The confounding variable in here is more people swim, right? Hotter weather, warm weather causes ice cream sales, yet at the same time, people go swimming. So the confounding variable is actually the weather here or the heat outside. People who own a yacht are more likely to buy a sports car. Okay, well, again, you don't go down and buy a yacht and they don't give you a sports car on the and say, "Oh, here's your car. You get this too." It's wealth, right? The confounding variable here is the amount of money that you have. And if you have enough money to buy a yacht, then you more than likely have enough money to buy a sports car, and maybe you want one. Air pollution is higher in places with higher proportions of paved ground relative to grassy ground. Well, it's more than likely not the paved ground causing the pollution. The ground is paved for a reason because of all of the cars and vehicles and things like that. So the pollution is probably from the automobiles or the trucks or the trucking industry that is associated with the paved ground. And of course, the loss of the grass scape or the soft space doesn't help that either. People with shorter hair tend to be taller. Wow, this is a good one, right? Okay, so if I have shorter hair, I tend to be taller. Well, if we look at the historical data between men and women, men do tend to be taller in society than females, and it's just the way our genetics are made. Men tend to have shorter hair than women, so we could say that gender is the in between here and not simply the hair. And it only happens to be that during this particular time in our lives that men tend to have the shorter hair and they tend to be the taller of the two. And we could come up with plenty more than just gender. So let's talk experimental versus observational studies. So to start, an observational study is a study in which the researcher does not actively control. Big time, right? Does not actively control the values of the variable, but simply observes the values as they exist in nature. I go down to the mall, I sit myself down on a bench, and I actually love to do this. And at Christmas time, when my wife wants to go shopping, I like to sit on a bench and just simply watch people because they are interesting. That's all I got to say. So if I were to sit there and I were to maybe record some kind of data, how many times a person is walking by me on their cell phone, how many times I'm in a restaurant and two people are staring at their cell phone instead of talking to each other at dinner. If I were to observe these things as they naturally exist, I am in an observational study. If I'm in an experimental study, I'm actively controlling something. So now I am in charge of a laboratory style setting in which I can make something happen. I can control the temperature. I can control the time that you eat. I can control the loudness of the television set. I can control something, and then from that measure something else. In an observational study, there are almost always confounding variables. Probably should highlight that for yourself, right? Almost always gonna have a confounding variable in an observational study because you don't control anything. They can almost never be used to establish causation. Causation will not come out of an observational study. It would be super rare for that to even take place. Here goes a piece of data that was collected from U.S. Social Security Administration between 1991 and 2009. And what it shows in the yellow line is that the housing price index rose along the trend line that you see from 1991 to 2009. So you see it took a sharp increase here, and then it kind of made a small decline. The black line are the number of children who were named Ava. So babies were named Ava were really, really low in 1991, but they increased almost identical to the trend line of U.S. housing market, and then they took the same decreasing line. So the question would be, did people naming their babies Ava cause the housing market to increase and decrease? Well, obviously not, but are they associated? Well, they are, clearly. I see them. They are associated. Is there a confounding variable in there? Yeah, there's got to be a confounding variable in there. What could it be? Well, maybe that particular bubble of people who were driving up home indexes or buying homes happened to be on a trend of naming their children Ava between those years. We go through cycles of names in this country, and we go through cycles of housing in this country. We go through cycles of I have to own a house to I don't want to own a house. And that cycle goes up and down continuously. And we can always find some piece of data that's going to follow along with some other piece of data for some type of association. But again, this is an observation. There was no controlled effect of anything here. It's just, hey, this is what I saw. When we talk about randomization is important because it helps us eliminate that variable, that confounding piece we're talking about. So in a randomized experiment, it says the explanatory variable for each unit is determined randomly before the response variable is measured. And I'm going to have you underline that. Before the response variable is measured. Okay? So something's going to happen randomly. That's the experimental part of the explanatory. And then before the measurement takes place, this randomized experiment part has happened. So I randomly chose who got this explanatory part. The different levels of explanatory variable are known as the treatments. The different levels are known as the treatments. You may get the treatment of a placebo. You may get the treatment of the actual drug. Randomly divided the units into groups and randomly assigned the different treatment groups. So 2 levels of randomization here. 1, you randomly get chosen to be in group A or group B. Inside of those groups, you randomly get assigned to be into the treatment group. If the treatments are randomly assigned, and the treatment groups should all look similar. So in order for this to take place, I lose the confounding variable. I break the confounding variable portion of this because group A was randomly chosen, group B was randomly chosen, and the explanatory was randomly chosen inside of each of those groups. So I eliminate that effect of having that third confounding variable, if you will. If a randomized experiment yields a significant association between 2 variables, we can establish causation from the explanatory to the response. This is a big statement. So I have a randomized experiment. I have significant association about the 2 variables, meaning the explanatory and the response. And from that, if I have that without interjection of bias, I can establish causal effect. It says that randomized experiments are powerful and they allow us to infer causality. It's only randomized experiments that allow us to infer causality. Remember, an observation never, ever, ever will. So we have exercise in the brain here. And a study was found that elderly people who walk at least a mile a day had significant higher brain volume or gray matter and significantly lower rates of Alzheimer's and dementia compared to those who walk less. The article states walking about a mile a day can increase the size of the gray matter and greatly decrease the chance of developing Alzheimer's disease and dementia in older adults. Is the conclusion valid? Well, first of all, we have to notice a couple of things. What do I notice first? Well, the first thing I notice is that this is an observational study. Well, guess what? When you have an observational study, you can never, ever, ever infer causal effect. You can say there's an association. So up here, I can clearly say it appears that walking about a mile a day can help with gray matter, but I can't say that it does help with gray matter. So my validity for this has to be no. It is not valid because you can't apply causation. And again, all of our data is taken from a source. This was taken from MSNBC. Now let's take another one. A sample of mice were divided into two groups. One group was given access to exercise wheel and the other group was kept sedentary. So you can see that we have randomly divided our groups. Part of them get the wheel and part of them get sedentary lockdown. Poor mice. First of all, it's an experiment. Okay? It is an experiment. It is a random experiment. It says the brains of mice and rats that were allowed to run on the wheel pulsed vigorously, newly born neurons, and those animals then breezed through mazes and did other IQ tests of rodents. Compared to the sedentary mice group, is the evidence that exercise causes an increase in brain activity and IQ tests, at least in mice? It has to say that because it can't say people because we didn't do it on people, we did it on mice. Well, first of all, did we meet the criteria? One, was it random? Yes. Two, was it an experiment? Yes. Did we have results that were significantly different? Yes. So the answer is yes. We are allowed to put causality on this because it meets all of the criteria that we have implemented. In order to randomize something, we have a couple of different options. One, we can randomize a sampling when we put all the names and numbers into a hat. We talked about that. Two, we can put names and numbers on a card. We can shuffle them and deal them out to the cards as many piles as there are treatments. Three, we can use technology. If we have to have some kind of randomness, something like this has to take place. We can't just simply let people choose groups, or we can't just put our friends in groups, things like that. We're going to talk about knee surgery here. There's a wily kind of question. Researchers conducted a study on the effectiveness of a knee surgery to cure arthritis. It was randomly determined whether people got the knee surgery. Everyone who underwent the surgery reporting feeling less pain. So the first question is, okay, is this an experiment or is this an observation? Okay, so let's go back to it. Researchers conduct a study on effective neurosurgery. It was randomly determined whether they got the knee surgery. Okay, so it was randomly determined. So it's an experimental value. So we would experiment here, and everyone who underwent the surgery reported feeling less pain. Okay, is this evidence that the surgery causes a decrease in pain? Okay, well, first of all, we have a couple of things going on here. We don't have a control group who did not get the surgery. It said everyone who underwent the surgery would feel less pain. So in this, we don't have a control group of, for instance, we need somebody who got maybe a sham surgery and somebody who got a real surgery. We have this effect that when people, we call it the placebo effect, that if people feel they get something, even if they did not get it, that they report back that things happen to them. For instance, just simply putting a scalpel mark, putting you under anesthesia, putting a scalpel mark on you, sewing you back up, and bringing you back out without doing actually anything at all. Some people would report back feeling less pain because of that. They would feel a placebo effect from that. So, is this evidence that the surgery causes a decrease in pain? No, we needed a control group. There was no control group up here between it. It was everyone who felt that this was less pain. And here's the control group discussion. When determining whether a treatment is effective, it's important to have a comparison group known as the control group. Sometimes I call it the match pair experiment. It isn't enough to know that everyone in the group improved. We need to know whether they improved more than they would have improved without the surgery. So we need to have a group of people who think they got the surgery but actually didn't get the surgery. All randomized experiments need either a control group or two different treatments to compare. In ours up here, we had a treatment to compare. Right here, it says in the knee surgery study in the control group, they were not put under and cut open, but the doctor did not actually perform the surgery. All of these patients reported less pain. So again, we need to have two different groups. Okay, and this was described back in 2000 in the New York Times. It goes on to talk about the placebo effect. Often people will experience the effect they think they should by experiencing, even if they aren't actually receiving the treatment. This is the placebo effect. Well, there's a study out there floating around that 75% of the effectiveness of an antidepressant medication is due to the placebo effect. So let's talk placebo and blinding. We're almost done with this chapter. Doing pretty well. There's quite a bit in this ending chapter of 1.3. The control group should be given the placebo. So when you think about who's in control or what group you're controlling, they're getting the fake treatment. You're controlling them from the actual treatment. A fake treatment that resembles the active treatment as much as possible. Using this placebo is only helpful in participating those who don't know. Now, if we have a single blind experiment, remember in a single blind experiment, the person who is the participants are the ones who don't know, but the researchers still know. It's definitely better to have a double blind in which neither the participant nor the person recording the results has any idea who's in which group. Sometimes facial expressions, the way you look at somebody is going to give away possibly what group they're in. Are you getting this medication? Are you not? Some people just can't control their facial recognition. Here goes a study, and this is a green tea prostate cancer. It says a study was conducted on 60 men with pin lesions, some of them which turned into prostate cancer. Half of these men were randomized to take 60 milligrams of tea extract daily, while the other half were given a placebo pill. So we definitely have a study, and we definitely have randomized them, and we have a control group who's getting a placebo pill, and then we have a treatment group that's going to take the 600 milligrams of green tea extract. But they both think they're getting the pill that has something in it. So, questions. Was this an experiment or was this an observation? Well, this was definitely an experiment, right? Because we split them. The study was single blind, double blind. Now, I wouldn't tell you that it's real clear, but if it doesn't talk to me about somebody knowing something, then it's a double blind. After 1 year, only one person taking green tea had gotten cancer, while 9 taking placebo had gotten cancer. That is a distinguishable difference. Okay, that's important because remember, if it came back and it was 4 and 5, then it would be okay. Well, it's almost the same. Exactly. It's 1 versus 9. A difference this large is unlikely to happen by chance. Can we conclude that green tea really helps prevent prostate cancer? And the answer is yes. We have an experiment. It was done in a random manner. We had a control group. We have very distinguishable results that are different from each other, and we can conclude causality from that randomized experiment. The types of randomized experiments. Randomizing cases into different treatment groups is called a randomized comparative experiment. When we do that, we're just simply randomizing the different experiments into different groups. We can also give each treatment to each case and just randomize the order in which the treatments are received. This is called match pair. It's not incredibly important you remember these, but it's more important that you understand we're randomizing how the experiments are given out. Either is valid in a randomized experiment. Really, what you need to recognize and take away is it's got to be experimental. In that experimental, it has to be random in the assignment of the group, and it has to be random in the treatment. Why not always randomize? Well, sometimes it's ideal. We want to have it, but we can't get it done because maybe it's not ethical or not possible. Often you have to do your best so that data comes from an observational study. Here's an example. Wanted to do research for the Supreme Court cases as to whether the preferences for minorities in university admissions helps or hurts minority students. We can't take minority students and place them into a certain setting which is going to hurt their standing in education. So therefore, it would be unethical for us to do that. No different than for us to test asbestos and to take some people and put them in a room full of asbestos and some other people and put them in a room not full of asbestos. It would be non-ethical for us to do that and measure that. So that would have to be an observational kind of thing. Here's a nice data chart to kind of think in your mind. First of all, was the sample randomly selected? We're looking for yes. If it was randomly selected, it's possible to generalize to the population. Generalize, make an association, okay? Was it the explanatory variable randomly assigned? So once you did this, once you randomly select the sample, now let's move on to step 2. Did you, oops, that was too much. I gotta make that go away. Delete. There we go. Did you randomly, it keeps doing it to me. I'm sorry. I'm not going to do it. Did you randomly assign the variable? Yes. If that, you can make a causality statement about it. Okay. Causality. I'm going to try it one more time. Boom. Oh, look at that. Too much. It's going crazy on me. I'm sorry. 2 fundamental questions in data collection. The 2 fundamental questions are, did you take a random sample? And did you apply a random experiment? If you did these things, then your data is going to be a valuable piece of data. Doing randomized experiments on a random sample is ideal, but rarely achievable. If the focus of the study is using a sample to estimate a statistic for the entire population, you need a random sample. So that's a must-have right there. You must get a random sample. But you do not need a randomized experiment. Okay? Example, election polling, things like that. If the focus of the study is to form causality, if you want to say that green tea causes people not to get cancer, you need to have both a random sample and a randomized experiment. Drug tests have to meet both criteria. Talking about who's going to win an election only really needs to meet one of the criteria. Associations do not imply causations. In observational studies, we can almost always exist, so causal or causation cannot be established. Random experiments involve randomly determining the level of the explanatory variable. Remember, that's the one you deliver first. The X happens first. Randomized experiments prevent confounding. Control groups are necessary. Remember, you have to have a control group if you are going to make a differentiation between the experimental group. And the placebo effect exists, so therefore placebo and blinding should be used. Blind, double if possible. This ends chapter 1. When we come back, we'll be entering into chapter 2.